Très bien, l'enregistrement a commencé, donc ça veut dire que c'est l'heure et on a le plaisir aujourd'hui d'accueillir Cesnavicius, pardon. Pendant l'exposé, je pense que Cesnavicius sera content d'accueillir vos questions et vos remarques, donc n'hésitez pas à les poser aussi durant le temps de l'exposé. Cesnavicius alors c'est depuis 2017, je crois, c'est un spécialiste où ses domaines de recherche portent sur les variétés algébriques et leur homologie. Et il va nous présenter aujourd'hui, nous raconter les travaux de Collard, Lieblich et Olson sur comment reconstruire des variétés d'après leur topologie. Donc, merci et puis bon exposé.
Thank you very much, and for the introduction, and thanks also for the invitation to give this talk at Seminar BOURBAKI. The work I would like to discuss is that of Collard, which is a recent preprint from last year, and builds on earlier work of Lieblich and Olson. And the main question of these works is to what extent is a variety determined by its underlying topological space. So the basic question, perhaps well, naive a priori, but actually quite deep a posteriori, is whether an algebraic variety X over a field K, is it perhaps determined by its underlying Zariski topological space, which I will denote simply by like so. Well, post in this generality, the answer is surely no. One needs further conditions on X, and I mean a priori perhaps one does not expect the answer to be positive anyway, based on numerous examples that I'm about to discuss. So first of all, the answer to the question posed like that is surely no. Although the Zariski topological space X does determine a number of invariants of X. For instance, it does determine the dimension of X, the length of the maximal chain of specializations between points of X, and of course, it also determines the relation of specializations between those points themselves, between various points of X, as well as other invariants. But the answer is to the question is known. So let me begin by discussing examples of why it is known. Well, first of all, I mean the underlying Zariski topological space does not see non-reduced structure of schemes does not see nilpotence. So I mean, perhaps, I mean, for some people an algebraic variety is required to be reduced, so this is a moot point. But anyway, I'll just comment that to expect a reasonable answer, one has to require X to be reduced for sure. And I mean, a slightly an observation of similar vein is that if X is not semi-normal, it's slightly technical condition which has to do with universal homeomorphisms, then again the answer has to be negative, because then there are some varieties which map to X and are homeomorphic to X but not isomorphic. So this reducedness can be weakened somewhat to be less tautological. But anyway, another point is that by looking at low dimensions, the answer suggests itself to be negative. For instance, if one has an integral curve over this field K, then its underlying topological space basically sees only sees the cardinality of the field K, because I mean, Zariski topological spaces of algebraic curves are particularly simple. Every finite set of closed, I mean, the closed subsets are the entire curve itself, or finite sets of closed points, and curve being integral is a unique generic point. And there's no rich algebra geometric structure such as genus or real geometry of the curve that is seen from the Zariski topological space alone. So, well, from this, one could gather that at least one needs to require X to be a surface to hope for a positive answer if one still insists that the answer could be positive. But, well, as slightly, I mean, certainly more surprising examples were constructed by Wiegand and Krauter in the 1980s, who showed that for surfaces, more specifically for projective plane over the algebraic closure of a finite field, its underlying Zariski topological space is actually homeomorphic to its counterpart for a projective plane defined over an algebraic closure of a different finite field. So, well, at least if one does not fix the field K, then this example, which perhaps is surprising because after all, P and P prime have nothing to do with each other, yet these projective spaces look identical from topological point of view. So anyway, one needs to at least either require X to be of dimension at least 3, although from the sequence of examples, it's somehow, I mean, so far we haven't seen any positive evidence to the answer of the question being positive, or one needs to avoid positive characteristic. Perhaps this pathology of projective spaces is something of positive characteristic. Okay, as a final example, let me remark, actually it's more of a remark than an example, let me remark that actually Hochster, he completely classified topological spaces that appear, that underlie schemes. So a topological space T is of the form, is a Zariski topological space for some scheme S. Well, let me actually start with affine schemes. So for an affine scheme S, if this topological space T is spectral, this is purely axiomatic condition. It has to do with, for instance, the topological space has to have a base for topology consisting of quasi-compact opens, and every reducible closed subset has to have a unique generic point. For instance, I mean, if it's a spec of a ring, then certainly irreducible closed subsets correspond to closures of prime ideals, and these are the generic points. And anyway, so notion of spectral topological space is also a third condition, is purely axiomatic, and one knows that affine schemes, their underlying Zariski topological spaces are precisely the spectral topological spaces. And if one drops affineness, then if T locally looks like a spectral space, then it occurs as an underlying topological space of a scheme. So anyway, Hochster completely understood, completely clarified the question of which topological spaces arise as topological spaces of schemes. And this underlying topological space of a general scheme is actually, I mean, in general is locally spectral, but it's even spectral if S is quasi-compact and quasi-separated, for instance, if it's a variety over a field. And so one gets a somewhat surprising conclusion that if one takes the projective space, for instance, or any variety really over a field, then the underlying topological space is spectral because it's S is quasi-combined, quasi-separated. And by Hofstede's classification, actually, this underlying Zariski topological space is also shared by some affine scheme. Well, that affine scheme, of course, need not. It's just it's just spec of an arbitrary ring. It not be that of a variety over K or over any field for that matter. So. So this work of Hofstede suggests that I mean, restricting to varieties is reasonable if one hopes for any kind of positive answer, because otherwise the question is completely understood and in fact offers somewhat surprising phenomena. Well, so in view of these examples, the result of Kolar that is the subject of this expose came as somewhat of a surprise. The precise statement that I'll discuss in this talk is that if one has a normal geometrically integral projective varieties X and X prime over a field K, or in fact, well, let me require right away that these varieties are of dimension at least 4, so that we're away from the low dimensional phenomena that we discussed just a moment ago, and so these varieties are over a field, or more generally over possibly distinct fields K and K prime, and we require those fields to be of characteristic 0. Again, positive characteristic, there's also Frobenius, which somehow is a universal homomorphism. Anyway, so the main result is in characteristic 0. Then, in fact, under these conditions, every homeomorphism of the underlying topological spaces from X to X prime, it underlies a schema isomorphism, or a schema isomorphism from X to X prime. Effectively, under these conditions, normal geometrical integral projective varieties of dimension at least 4 over, say, complex numbers, or more generally over any fields of characteristic 0, they are completely determined by their underlying topological spaces. And this formulation about the schema isomorphism really is equivalent to saying that by taking global sections, because X and X prime are geometrically integral, it's equivalent to saying that there exists a field isomorphism K to K prime, perhaps called iota, and then variety isomorphism of X base changed along iota to K prime and this X prime. That's just a different way of saying the same thing effectively. So this is a result that whose argument I'll try to sketch in this talk. But before getting there, let me just make a couple of remarks about possible about improvements that one knows. I'm not stating the most general form for the sake of simplicity. I'm focusing on the statement that already contains all the main ideas. But for instance, Kolar also shows that one can allow dimension to be free. One could consider free faults as well, granted that the fields K and K prime of characteristic 0 happen to be finitely generated over Q, so in particular countable. And in further work, in further joint work of Kolar, Lieblich, Olson, and Sawin from from last year as well. They show that surfaces dimension, in other words, varieties of dimension 2 are also okay. Well, certainly one needs to include positive characteristic, but more generally, if K is algebraically closed and uncountable. Perhaps I should say K and K prime are algebraically closed and uncountable. Well, perhaps the result is when K is equal to K prime, but let me not get into that. So there are some sharpenings, but the main result we'll discuss is this one, dimension at least 4, and then normal geometrically integral projective varieties are determined by their underlying topological spaces, granted the characteristic is 0. Now, with these results at hand, so the answer to the question that I posed at the beginning of the talk is then evidently positive, at least for a large class of varieties, in spite of these examples. And Kolar goes further to formulate a general conjecture, which so far is open, which is a general prediction of when precisely the answer should be positive. So if one restricts to semi-normal varieties, this is just to avoid these universal homeomorphisms that I've alluded to, in particular to reduced varieties. So semi-normal geometrically reducible varieties X and X prime of dimension at least 2, so surfaces should be okay, over fields K and K prime. Well, we certainly need to exclude positive characteristics somehow, right? Because of that projective plane example. So we require that at least one of those fields is of characteristic 0. Then every homeomorphism between the underlying topological spaces again underlies a schema isomorphism from X to X prime. And again, yeah, like so. In particular, K prime is also of characteristic 0 then. All right, so that's these are the results I'll discuss, and let me proceed to overviewing the overall structure of the argument. What are the main steps before proceeding to actually discuss those steps in somewhat more detail? So the main idea, the main idea is to study divisors on X. Divisors D on X. So a divisor is just it may be viewed as a formal linear combination of points of codimension 1 on X with coefficients with integral coefficients, and so that's an abelian group. It's a free abelian group on codimension 1 points of X, and the effective divisors is a submonoid consisting of those linear combinations where the coefficients are non-negative. And both of these fellows, the divisors and the effective divisors, they are determined. Certainly, they are determined entirely by the underlying topological space. By the underlying topological space X, because it's just free abelian group or monoid on the codimension 1 points, and codimension is something determined by underlying topological space. But notions associated with divisors such as ampleness or base point freeness or all these kind of more geometric notions, they are not a priori determined by the underlying topological space, and the whole kind of name of the game is to show that actually many of them are, and to show how they are actually determined by the underlying topological space under suitable conditions. So for x over k as in the theorem, main theorem, so normal, geometrically integral, projective of dimension at least 4, projective of dimension at least 4, and k is still of characteristic 0, the argument proceeds by first taking in the underlying topological space and showing it as a first step that one can actually recover a certain equivalence relation on divisors, or more precisely on a set of irreducible ample divisors on X, and in particular, one can recognize ampleness of an irreducible divisor purely from the underlying topological space, and more generally, one can recognize this linear similarity relation, which is defined as follows. So two divisors D1 and D2 are linearly similar if, I mean, this is just a definition, if some positive multiple of n1 is linearly equivalent to some positive multiple of D2, like so. So if positive multiples of di are linearly equivalent, then the di are said to be linearly similar, and this is this is coarser evidently than linear equivalence, and it's the first kind of relation that one recovers in the proof. So the first step of the argument is to recover this relation between irreducible ample divisors. The second is to use this, and the second step is actually a lot longer than the first, is to recover the full relation of linear equivalence between effective divisors on X. Well, and I mean, effectively between all divisors. Any divisor is just a difference of effective divisors. So that's actually the longest part of the entire proof. And the last step is to take the datum of the underlying topological space with the datum of linear equivalence between effective divisors and recover the variety X itself. And this last step is what has been known prior. So this step is due to Lieblich and Olson. And somehow served as a spark for Collard's work. And let me just say that somehow in this step, the ultimate result that recovers the projective variety, roughly speaking, is the fundamental theorem of projective geometry, which is a result from 19th century, which says that which characterizes projective spaces in terms of a set of their points and lines and incidence relations between points and lines, and intersection properties of lines that they satisfy. Lieblich and Olson prove a version of this fundamental theorem of projective geometry that is suited to their needs, and they apply it to the projective space given by projectivizing the global sections of certain very ample line bundle on X. So here H is a suitably chosen very ample line bundle on X, and one also considers its image. It's a very ample H is a divisor, and O is a very ample divisor on X, and one somehow applies their version of the fundamental theorem of projective geometry to these projective spaces for every m greater than 0, and they, well, I mean, this is very rough, but somehow in this way they recover the projective embedding because X is projective. It's isomorphic to the proj of the direct sum over all non-negative m of these global sections. That sits in the projective space, which is just a proj of the tensor powers of the first of just O of H to the mth tensor power. So that's just some projective space over K, and somehow okay. So by, I mean, for somehow roughly speaking, in this way, they are able to compare these projective embeddings for X and X prime and show that X and X prime really match, and to show that these projective spaces match. That is where the linear for X and X prime match. That is where the linear equivalence comes in. So the points of this projective space are given by effective divisors on X that are linearly equivalent to m times H. The global sections of a line bundle associated to a divisor, non-zero global sections up to scalar multiples, they correspond to divisors linearly equivalent, to effective divisors linearly equivalent to the given one. And so the points of this projective space are interpreted in this way, which is how the linear equivalence of effective divisors becomes relevant for this reconstruction step. And of course, one needs to isolate also sets of lines in this projective space with which to apply the version of fundamental theorem of projective geometry, and that's somehow where a lot of the work lies. These are the so-called strongly definable lines that they consider, and the whole point is to show that these lines are determined purely by linear equivalence of effective divisors and underlying topological space. So I'm not doing full justice to their work, but let me just leave this step at that, and for the rest of the talk, focus on these on step number 1 and step number 2, which well, at least step number 2 is somehow longer. So let me begin for this by discussing this first step number 1, which is the linear similarity relation. So we just depart from the underlying topological space, and we want to determine linear similarity of ample divisors. And so for that in particular, it's implicit in this kind of assertion that we can determine that it's implicit that we can topologically recognize ampleness of reducible divisors. And so let me begin by just giving a precise topological criterion to Collar of how to recognize ampleness. So if one has an irreducible divisor H on X is ample if and only if for every effective divisor, D on X which is just a closure. I mean, just a closure of codimension 1 point. So it's a topological, well, it's a closed subset of pure codimension 1. So it's topological notion, and distinct closed points x and x prime, which do not lie on this divisor. The condition is that there is another effective divisor. There's an effective divisor h prime, such that the intersection of h prime with this d just on underlying topological spaces is the same as the intersection of h with d. And moreover, the point x lies in h prime, but x prime does not lie in h prime. So the condition is purely topological. For every effective divisor d, there is this other, and distinct closed points, there is this other divisor h prime, which intersects d in the same way as h does, and contains x, but does not contain the other point x prime. And just to illustrate the ideas, let me sketch the proof, or let me at least try to convey the idea of the proof. The harder direction is to show that H is ample from departing from this condition. If one already knows that H is ample, then somehow multiples of it have many linear effective divisors linearly equivalent to it, basically by EGA free, and one can certainly find such an H prime, which on given closed agrees with the section of associated line bundle that cuts out H and passes through X, but not X prime. So the more difficult direction is to show ampleness from this condition. Now, for ampleness, there are many criteria that one could try to use. For instance, Kleiman in the 1960s wrote a paper on numerical criteria of ampleness, and so he showed that showing ampleness basically requires producing, well, I'll put in quotation marks, many sections, many effective divisors. Basically, he showed converse to that result of EGA3, which is, well, many effective divisors H tilde, which are linearly equivalent to some multiple, to a variable multiple of H. So here, this N does depend on H tilde. And many just means that H tilde is required to contain 1 point, but not contain the other, where the points vary, X and X prime, as in a statement of this criterion, really. So, okay, so given this, how do we proceed? So given X and X prime, which are what appears in the many in quotation marks, one uses the Bertini theorem. Use Bertini theorem to choose X is after all projective, so it has many effective divisors. So we can choose an effective divisor D such that D is somehow sufficiently general so that the induced map on divisor class groups, divisors up to linear equivalence, is injective. So this is the Lefschetz theorem for divisor class groups, and it was established by so for divisor class groups, and this was established by Ravindra Srinivas in 2006. Actually, this result uses characteristic 0 assumption on X, although one could expect that there are variants also in positive characteristic. It also uses the dimension assumption. So D has to be of dimension at least 2, at least a surface, so X at least of dimension 3. So anyway, by using Bertini and using this Lefschetz theorem, one can find a divisor such that the class group injects into a class group of a divisor. And moreover, the intersection of H and D is reducible. After all, H is reducible, so cutting it by general hyper surface section will still be reducible. Then this condition, which I'll call star, this condition about there existing H prime with the same intersection and so on, this condition star implies that in fact some multiple of H prime is linearly equivalent to some multiple of H for some positive and i's. Well, why is that? I mean, H intersects D irreducibly, so this intersection of H with D is an irreducible divisor on D now, and so therefore H prime intersect with D is also an irreducible. Well, it's a multiple of an irreducible divisor. Viewed as a scheme is a multiple of an irreducible divisor on D, as is H intersect with D. And those divisors have the same underlying topological space. So really, they just differ by what constant is in front of that irreducible divisor. So by choosing some n1 and n2, we can make them the same. We can make these intersections give the same class in the class group of D, but because H and H prime begin life over X, and because this map is injective, we get that actually those multiples are then linearly equivalent on X itself. So that's somehow the mechanism in which this Lefschetz theorem for class groups is relevant. And at this point, one may simply choose the H tilde required for Kleiman's criterion to be n1 times H prime, and then n is just n2. So roughly that's how this argument goes. How one recognizes topologically ampleness of irreducible divisors. All right. So in a similar vein, Kolar recognizes linear similarity of irreducible ample divisors as promised as is the first step of the proof. So topological recognition of linear similarity goes as follows. Let me just give the criterion without entering the proof. The proof really uses similar technique. It again uses the Ravindra-Srinivas theorem, but in fact, I'll comment there's a difficulty that requires further work. Anyway, so the criterion is this: irreducible divisors H1 and H2 on X such that one knows that H1 is ample, as is a topological condition, as we just saw. So such irreducible divisors are linearly similar. In other words, they are equivalent under this linear similarity relation if and only if for all irreducible closed subschemes subvariety Z1, Z2 of X, or just irreducible closed subsets really, of dimension at least 1, and which are disjoint, Z1 and Z2 do not intersect. If for any such there is an irreducible divisor, and there's an irreducible divisor H prime on X such that the intersection of H prime with Zi is the same, topologically is just the same as the intersection of Hi with Zi. So again, just by comparing topologically intersections with variable disjoint irreducible closed subschemes of positive dimension, one is able to recognize that H1 and H2 are linearly similar. Roughly speaking, the game is similar to the previous proof. One needs to choose the Zi this EI appropriately, and they're chosen to be suitable complete intersections of a fixed ample divisor. One uses Bertini theorem, of course, and one uses this Ravindra-Srinivas theorem, except there's one wrinkle. Well, if for the Bertini, for the Ravindra-Srinivas theorem, as I mentioned, D should be of dimension at least 2. So Z1 and Z2 should be of dimension at least 2 if one hopes to use it in the same way as in the previous argument. But if X is of dimension precisely 4 and not 5 and higher, then of course one cannot fit inside sometimes one cannot fit two surfaces inside a fourfold, which would be disjoint, which kind of poses a problem. And so one actually to 3-dimension 4 is a lot more subtle. It requires arithmetic inputs. One uses some result of Néron from 1950s about specialization of Picard group. The argument becomes a lot more technical because of that in dimension 4. But this is anyway. This is the criterion. Regardless of dimension being 4 or higher, the criterion is the same. It's just that the proof is more complicated in dimension 4. So let me then proceed to step 2. In fact, step 2 kind of goes in 2 stages. Now we discussed how to recognize linear similarity of reducible ample divisors from the topological space. And step 2, one recognizes, one takes that and one recognizes a lot more. So for this, I'll fix, basically for the rest of the talk, fix an irreducible ample divisor H on X. So that's topological by preceding step, and more generally, so by the previous step, the following notion, which is purely topological, and that is the notion of linkage. So the idea is to study linkage on between subvarieties of X to learn scheme theoretic properties of their intersections. So what is linkage? Well, for this, let Y1 and Y2 be integral closed subschemes, integral closed subvarieties with 0-dimensional intersection. Subvarieties, in fact, of positive dimension with 0-dimensional intersection. Then irreducible divisors. H1 and H2 on X, which are linearly similar to this given H. So they all belong to the same linear similarity class of the given irreducible ample divisor. These are H-linked for these irreducible divisors H1 and H2 are H-linked for the subvarieties Y1 and Y2. And this is a definition. If and only if there exists an irreducible divisor H tilde on X which is again is linearly similar to H, that's still being purely topological condition as we saw, and such that the intersection of H tilde with Yi topologically is the same as the intersection of Hi with Yi. And one says that H linking of Y1 and Y2 is free if there exists a finite subset, sigma of the union of y1 and y2, such that all h1 and h2 as above, which in addition are required to be disjoint from the sigma, are H linked. If there's somehow no obstruction away from the sigma of linking, are H linked for y1 and y2. Okay, so well, this is effectively a purely topological notion of how divisors intersect. These yi's can be glued to a single divisor on X, and the key insight, I mean, in the step, the key insight of Collar is that this linkage, properties of linkage, its properties encode. It's a purely topological notion, but they encode properties of the intersection between y1 and y2, and of schematic intersection. So they encode schematic properties of this intersection. So and why is that? Well, roughly speaking, well, perhaps let me first give an example and then comment. So for example, H linking of y1 and y2 is free if and only if this intersection is reduced. And so reducedness is something highly non-topological. If the zero-dimensional intersection is reduced and the induced map on global sections, like indicated, like so, from one of the yi's to the intersection, is actually an isomorphism for some I. So by studying linkage, one can recognize reducedness with this extra additional bonus condition, maybe which one doesn't want a priori, but anyway, one can recognize reducedness of the intersections just by asking why the linkage of these y1 and y2 is free. And well, roughly, why is this so? I mean, at least so these HIs are given by global sections I mean, their intersections with yi. HI is linearly equivalent to some multiple of H, and so they're given by global sections of this kind of line bundle on yi, and the whole point is then patching these global sections over on the intersection of y1 and y2. And then later one can lift them to global sections to entire X, and that global section will cut out the required H tilde. And so then the study of these maps, or study of these restriction maps, is particularly relevant, especially if one replaces here by units, because this is what allows patching. If one can adjust the sections on the yi of the line bundle such that they match on the intersection, and one can glue them together and obtain a section on the union of y1 and y2, and then that will be the kind of linking the section whose the zero locus of that section will be the linking. So anyway, the fine analysis of these is perhaps somewhat involved, but by studying linkage, Collar uses this underlying topological space and the linear similarity of irreducible ample divisors to recognize quite a fair bit of properties. So for instance, he can determine purely topologically, effectively, well, determine from this linear similarity relation between irreducible ample divisors whether this intersection is actually reduced. And we already saw with a little bonus condition, this is just equivalent to H linking being free, and one can remove that. So the idea removing that is to let y1 vary with same while still having the same intersection, at least topologically. And I mean, if one has the same intersection and the scheme is somehow more non-reduced, then there's just more. I mean, and you are able to patch the sections there, then you surely will be able to patch the sections on the reduced scheme because you just got rid of some nilpotents. That's roughly how this recognition works. And he is also able to determine whether reduced zero-dimensional closed subschemes Z1 and Z2 that happen to lie in a smooth locus of X, whether they are isomorphic over K. So effectively, if Z1 is a spec K1, or for some finite extension of K, and Z2 is a spec of K2, and both lie in a smooth locus, Collar is able to determine whether K1 is isomorphic to K2 just as an extension of K, just topologically, purely in terms of topological space of X. So one can determine also if Y1 is K smooth at the closed point at which X is smooth, at which X is K smooth. And moreover, actually one can determine the entire intersection theory basically with, well, the degree function with respect to H. One can determine the ratios between intersection numbers of D with the dimension of X minus one-fold self-intersection of H. Effectively, it's just the H degree of this divisor D. So for divisors D, if we have two such Ds, and these are just safe for effective divisors D, so that this intersection is positive and non-zero. So if one has two such Ds, then the ratio of these intersection numbers is then some number which is really just determined by the underlying topological space. And so even if this topological recognition of ampleness or linear similarity from the proof, it seemed kind of somewhat close to, I mean, perhaps it wasn't so unexpected given the proof, that just determining these intersection numbers is quite surprising, because after all, the intersections like that, I mean, there's a lot of non-reduced structure that encodes these numbers, and determining them from underlying topological spaces, at least a priori, to me, it seems quite surprising. So, well, so that's where I will leave this step of linkage, and I'll proceed to the second part of the step 2, which is studying topological pencils. So let me just let me actually just give an idea of how linear equivalence is eventually recovered. So the idea is that if one has effective divisors, say D1 and D2 on X with no common irreducible components. So these divisors are linearly equivalent if and only if there exists a rational K-morphism, dominant K-morphism, rational, so defined, I mean, on the dense open, towards a projective line such that D1 and D2 are distinct distinct K fibers of this pi, of this map pi, or perhaps I mean are closures of distinct, because the map is not everywhere defined. Then somehow we first look at maximal local definition, look at these K fibers, and then take closures in pi. And because every two K points of P1 are linearly equivalent, there is a rational function on P1 which has this simple 0 at one and simple pole at the other, then the pre-images will be linearly equivalent the effective divisors on X. And conversely, if one has linearly effective divisors on X, then they correspond to sections effective divisors, then they correspond to sections of the same line bundle, and the two sections of that give give a map to pi 1, a rational map to pi 1. And so these kind of maps are linear pencils, give linear pencils of divisors on X. And so the name of the game is the strategy is to show how to topologically recognize pencils, such pencils, and use this to then recognize linear equivalence. Okay, a priori, so the first step is then is to recognize pencils, and the key notion is that of a topological pencil. So to introduce that, I'll first make an auxiliary definition. If one has an infinite set of closed subsets of X, of closed subsets d lambda of the underlying topological space, Zariski topological space of X, then or really of any topological space of the base locus denoted by base P of P is the if it exists, is the closed subset B in X, if it exists, such that the pairwise intersections of these lie in B for all distinct lambda and lambda prime in lambda, and there exists a subset lambda prime which is cofinite, the complement is finite, such that the intersections of the d lambdas are actually equal to B whenever the lambda and lambda prime are in the capital lambda prime. So pairwise intersections are in B, and away on a subset which is essentially everything, the pairwise intersections are actually equal to B. Then a topological pencil. Okay, let me write in full. It's a definition after all. So a topological pencil on X is a set like so of reduced effective divisors d lambda on X, such that well, first of all but finitely many d lambda are irreducible. Jointly, the d lambda cover the closed points, of X. So there's plenty of them. They somehow sweep out the entire X, and the base locus of the family exists. Is of codimension at least 2, and each each complement is connected. The base locus does not disconnect the divisor. The main example of this, of such families, these are the algebraic pencils, which are closures. Well, which are just as in a basic example that I discussed above, which are closures of connected components of fibers, say over closed points, fibers over closed points of a dominant rational map to a curve, of a dominant rational map to some curve C, K map, of course. Yeah, so these fibers, their closures give a algebraic family of divisors parameterized by a curve, just as it was for divisors parameterized by P1. And let me close by giving a topological criterion. So the main, to make the strategy viable, one needs to recognize which of these topological pencils are actually algebraic, and to do that topologically. So the following is a topological recognition of algebraic, of those topological pencils which are algebraic, of algebraic topological pencils. And in fact, the criterion is quite simple. So a topological pencil P of divisors d lambda is algebraic if and only if there exists an infinite subset lambda 0 in lambda, such that all the degrees, all these intersection numbers like so, are pairwise equal for lambda being in this lambda 0, and these intersection numbers are something that we just discussed, that they can be determined topologically. Here, at least the ratios can, and so the equality can also be determined topologically. And so this criterion then gives topological criterion for when a topological pencil is algebraic, and there's further criteria of when the C that appears here is actually P1. One uses that to somehow put two given reduced divisors, which one wants to show linearly equivalent, which one wants to recognize topologically the linear equivalence. One puts them into topological pencils that share a common member, and one uses these criteria to effectively recognize linear equivalence of reduced divisors and then of all divisors. This, as in step 2, roughly speaking, that's how this step goes. First, one studies linkage to determine these intersection numbers, and one uses this idea of topological pencils to recognize algebraic topological pencils. One uses a Chow scheme here in the proof of this criterion, and then finally one puts divisors into such pencils with a common member and gets topological recognition of the linear equivalence. But I'm out of time, and so I'll stop simply with this.
Thank you very much. N'hésitez pas à poser des questions. Please ask questions. I'm sure there are many questions.
I can ask the obvious question, which is what is known in positive characteristic?
I think not very much, but one thing is known though. In this work of Collard, Lieblich, Holson, and Sawin, which they do show that this last step, this recognition of X, granted that one can recognize linear equivalence of effective divisors, this last step works also in positive characteristic pretty much. So that, and even, in fact, even X could be proper, not necessarily projective. So this part is seems okay, but the other arguments, I mean, the steps 1 and 2 is not so clear how, well, at least a priori not so clear how to make them in positive characteristic. There are some technical problems. I mean, this theorem of Ravindra-Srinivas is in characteristic 0, but that's maybe not really, surely that's not like the main obstruction, but many steps in 1 and 2, many proofs require characteristic 0, so it's less clear how to extend those.
Yeah, it seems the thing with the pencils is only true in characteristic. Well, is it true in positive characteristic?
Sorry?
The topological recognition of the pencil. Oh, sorry. The topological recognition of the pencils that are algebraic.
Yeah, there's subtleties with that as well. It's not wait, let me check. I'm not.
In your notes, you stated in characteristic 0.
I see. Okay, so that part is that part. The topological recognition of algebraic pencils does work in positive characteristic, but the linkage step does require characteristic 0, and also later when the two get combined to an actual criterion of linear equivalence, then that inherits the characteristic 0 requirement.
And I see the conjecture of Collard is always for varieties over fields. And is there any hope to have some statement for schemes that are not?
Yeah, I don't know, but one has to keep in mind these examples of Hofstadter where one has pathologies like that. So one certainly has to have something like finite type over something reasonable, maybe, or
yeah, I mean, you could say flat finite type over Z, and then you get this example. Obviously, you would need more, but
yeah, well, one could definitely pose such questions. It's just that, as far as I understand, there are few in the way of proved results of to really inform of what one could expect. But I think it's definitely reasonable to expect that maybe there could be a version of this over Z or so on. The base being a field is just the first. It's just a beginning, natural beginning step, but. Anyway, I don't know of a precise statement that one could pose.
Yeah, you mentioned that in characteristic P there is a Frobenius an obstruction to the theorem to be true as it is written.
Yes.
But yeah, are there other obstructions which are known? Is it reasonable to hope that up to Frobenius twisting the schemes are isomorphic, or are there other obstructions that we know already?
I don't know for sure, but I think it's reasonable. But my understanding is that it just not so much is known in positive characteristics, so it's not so clear what to conjecture precisely. Also, this example with okay, one would have to exclude surfaces for sure because of this kind of pathology, but maybe that's just a thing for surfaces. So one could one could expect somehow some meta statement that up to Frobenius and up to some normality issues, that maybe is the only obstruction, but that's just a speculation. I mean, there's not so much in the way of known results that would confirm this expectation.
Polar's result in characteristic 0 excludes surfaces, doesn't it? I mean, even though he conjectures that.
Yes, although so there is this result of Kolar, Lieblich, Holson, Sawin, where surfaces are also okay.
Sorry, I forgot. Okay, good point.
But I think there the field is actually fixed, not k is equal to k prime, and also that it's required to be algebraically closed and uncountable. But anyway, over complex numbers, it's surfaces. Okay.
So one would need more counterexamples in characteristic P, maybe to understand what happens.
Yes, but it's also not so clear that these counterexamples exist in dimension 3, right? It could just be that.
Examples of counterexamples.
Yeah. Anyway, it's definitely a very exciting direction. This the results that have just been established and that have not been expected previously. So there's definitely possible that there are things to be discovered in positive characteristic, especially.
D'autres questions? More questions? Est-ce que on aura un espoir de comprendre quelles sont les applications qui ne sont pas forcément des homomorphismes, mais entre les espaces topologiques X et X'? Est-ce qu'on pourrait
les algébraisés, homomorphismes entre variétés algébriques? Je sais pas. Once again, there's no clear statement that I could think of in this direction.
Et j'avais aussi une question. I had a question on the Oshers result. Does it construct explicitly the affine scheme out of the spectral topological space?
It's not very explicit. No, it's just some filtered direct limit of some algebra, finite algebras over Z. It's not. I don't think one can really understand these so explicitly. It's just it's a curious result, but it doesn't really tell you what that affine scheme is that's isomorphic to homomorphic to projective space, say.
Okay. And would the proof of Kogar's theorem will be easier if one assumes that X and X prime are just smooth varieties and not?
Yes, some parts would be easier. For example, so I didn't really get to stating the topological recognition of linear equivalence. Also, it is a little bit long. Anyway, it's in the notes. But here, this step of recognizing smooth points on, say, divisors or on subvarieties Y1, if X is k-smooth at that point. I mean, technically, if all of X is smooth, then the proof would be a little bit simpler, because somewhere in some of the statements, one first fixes some bad closed subset of codimension at least 2, which roughly speaking is a non-singular is a singular locus or something containing a singular locus, and then one works away from that. So one could get rid of such closed subsets, but it's not that the proof would simplify dramatically. It's just some technicalities that would be a little simpler.
So even with this extra assumption, the result is completely new.
Yes, yeah, definitely. That assumption does not see smoothness versus normality. It's, as far as I sort of see, it's just a cherry on top on this result. It's not really.
Okay. Okay, so
sorry,
okay,
I have a question. I have a
sure,
question. So did people expect such a result, even expect such a result before it was proved? Because I find it very surprising. So I even wonder how people could have thought that such a wonderful result could be true. So was it expected, or was it a total surprise? Or
my understanding is that it was a total surprise, so yes, there was this prior work of Lieblich and Olson, but this was purely about this step, that if you have linear equivalence of effective divisors, then you can recognize X. And well, I don't know for sure what Lieblich and Olson expected, but my somehow understanding is that perhaps one would have found surprising that one could actually get rid of this entirely and just go from topological space to X. And it must have been that Kolar had some intuition about the geometry and divisors and recognizing things topologically, that he envisioned that this could actually be possible. But I think the result did come as a surprise. All these examples, some of them quite surprising, point to the contrary, and there's no, at least a priori, there's nothing known. At least before this, there was nothing known, so it's kind of completely in the dark.
Thank you.
Mais donc il n'y a pas de lien avec ce qu'avaient fait Bogomolov et Tschinkel avant, et des gens comme Pop.
Oui, il y a un lien. Donc, le travail de Lieblich et Olson est lié avec ces travaux antérieurs. Donc, peut-être même que Lieblich et Olson sont inspirés un petit peu par ces travaux antérieurs qui s'appuient aussi sur le théorème fondamental de la géométrie projective. Et donc pour ça que peut-être cette étape, on pourrait dire, moins surprenante que l'autre. Mais oui, mais pour ceux deux, il paraît qu'il n'y a pas de résultats antérieurs.
D'accord, merci.
Très bien.
Est-ce que je...
Vas-y.
Again, it's a question about the surfaces. So there is this result that you mentioned of Kolar, Olson, Lieblich, and Sarin. That if the ground field is algebraically closed and uncountable, then the result holds. And is it definitely false? Well, it's false in characteristic P because of finite algebraic closures of finite fields, but over number fields, is it expected to be true, or is it expected to be?
I think so. From this conjecture, one would expect that it's true over number of fields.
Okay, it should be true. Okay.
Yeah. Yes.
And probably over the function field of a curve in characteristic P, it could be true as well. Or maybe wait.
I'm less certain. But perhaps extending it to number of fields is a problems of arithmetic nature somehow. For instance, this Ravindra Srinivas theorem uses a dimension assumption, and one needs kind of finer arithmetic stuff to really get to smaller base fields. So it's problems of this sort that intervene in characteristic zero. But in positive characteristic, I'm less sure if one.
Okay. Thank you.
Okay, thank you very much. J'ai l'impression qu'il n'y a plus d'autres questions. Je suis sûr que d'autres personnes pourront contacter Kestutis directement pour lui poser d'autres questions. Je propose de remercier encore une fois vivement Kestutis pour son exposé. Et je vous rappelle à tous qu'on a un deuxième exposé à 14 h par Clément Dupont et je vous encourage à venir y assister également. À tout à l'heure.
Merci. À tout à l'heure.
Merci, Kestutis. Super.